Okay, so now can people confirm that they can hear me?
Yes, sir, I can hear you.
Okay, good, wonderful. So again, thanks for coming. Thanks for joining us again. Today is the last such lecture I will give, and today I continue the story of the galaxy systems that I started yesterday, and there will be some overlap with some of the issues that have been dealt with already in large-scale structure formation, in gravitational lensing, in all that stuff. But of course, we need to look at this again in the context of galaxy clusters. And that is why there will be some repetition. And let me share my screen. Okay, so let's, I'll pause as I normally do to look at questions. So yesterday we talked about dark matter. Now, you've encountered this in the context of galaxies before, and yesterday also we looked at this issue of dark matter on the outskirts of galaxies, which you get from rotation curves, and the fact that even as you go, because normally galaxy sizes, if you look at just the distribution of stars, they stop at about 20, 25, 30 kiloparsecs, so the largest galaxies in radius. And one can map out the dark matter to very far away from the centers of galaxies using test particles. And one of the test particles I talked about was the neutral hydrogen that is emitted and detected in the radio, 21 centimeter. And that is bound to the galaxy, but it stretches out to much larger distances than the stars. There are other things too that people have used, which I'm not talking about today. For example, globular clusters. Globular clusters are bound to the galaxy. Their system of globular clusters goes out to, in fact, in our galaxy, the farthest globular cluster is about 130, 140 kiloparsec away. Which is bound to the galaxy. So there are galaxies there you can actually use those as tracers. The only problem is you don't know their orbit very well. And so you need many of them to make some statistical argument. Then there are other things. For example, there are the satellite galaxies that I showed you in the local group, the ones that are bound to our galaxy, the satellite galaxies, then these will be, those also can be used to trace the dark matter. But again, since we don't know their detailed orbits, there is an uncertainty about how much you can get from just the line of sight radial velocity of that particular point. Whereas for a continuous medium like the neutral hydrogen, you can do this. But this also is important in the context of groups and clusters, because this tells us that there is this contribution of the galaxy halo to the cluster dark matter. Now, let's look at, so these stretch quite a bit. But what I was saying is then the clusters themselves have quite a lot of dark matter. And this came from, as I mentioned yesterday, Zwicky's work in the 1930s, originally looking at the Coma Cluster after Hubble measured the first few redshifts of nearby galaxies and slowly started going out in distance. Zwicky, a few years later, had already measured the radial velocity using the same setup, the spectrograph of galaxies in the Coma Cluster. And he came to the conclusion that they were moving too fast if you assume that the mass of the cluster is the same as the mass that you see inferred from the light, which means that you see the light coming from the galaxies. You say, look, I know the mass of the sun is so much, the mass of the light of the sun is so much. So there is a ratio between the two, the relation between the two. Then I measure the entire light coming from each of these galaxies. I convert that into a mass based on our sun. And then he found that the amount of light calculated that way, amount of mass calculated that way, falls short by a factor of at least 100, given the fact that there's a dynamical measurement that you can make from these. So I'm going to take you through that little argument. It is based on the Virial theorem. You have encountered the Virial theorem before. And if you haven't, it is of course, in classical mechanics, in most classical mechanics books. The Virial theorem is introduced in Goldstein, for example. It's a big discussion on it, came from Clausius. The idea is as follows, that if you have a system of particles that are, where there's thermal motion in the particles, then twice the kinetic energy plus the potential energy of the particles, time averaged over a very large amount of time, not over individual orbits, but a time scale that is much larger than individual orbit time scales, is equal to this quantity, which is the second time derivative of the moment of inertia of the system, right? Half of that. So that is a very interesting quantity. And what we say in astronomical applications is that we will treat this as an equation of motion, time averaged over a long period of time for systems that are in equilibrium. So, for example, if you had this quantity, which is to the left of this equation, if the system is contracting or system is expanding, then this value is non-zero. But if you have a system that is in equilibrium, which is neither contracting, falling together for the first time, or expanding, then you can think about the moment of inertia to be constant with respect to time, and so this can be zero. And so this reduces to a very simple, and you can see what I is. I is the moment of inertia, is just a sigma of mr squared. And so if, for example, a system is not contracting or expanding, then that is going to be zero, the second time derivative of it. And so then this is reduced to an equation which is very simple: 2 times the kinetic energy time averaged over a long period of time plus the potential energy equal to 0. So Zwicky used this equation, 2t plus b equals 0. You might have seen applications of this in other settings, in other lectures. So once you have that, then you can say that, say you have a cluster, which you can assume to be spherical, and you have lots of galaxies of different mass in it, then the total potential energy of this cluster will be V. Total kinetic energy will be just half of mv squared, averaged over all galaxies. And remember, you only measure the radial component of each velocity of galaxies because you measure it from the Doppler shift. So you can use the argument that you often use in kinetic theory of gases, is that statistically, over a large sample, this will give you only 1/3 of the total kinetic energy. And so you can multiply that by 3. And so that gives you the total kinetic energy, and that is your T. Okay. How do you calculate the potential energy of a spherical system? We've done this in class. You know that you integrate from how to assemble mass in a cluster, a spherical system, by bringing shells from infinity and slowly assembling a uniform sphere of mass n. For the time being, assume it's uniform. You can actually then, you don't need to assume it's uniform. The shells themselves need to be uniform, of a constant, of a uniform density rho. The shells can be very thin, and then you can have m of r dm, and you can slowly assemble them, and you know that the final spherically symmetric value you get for the total gravitational potential energy of assembling a sphere of mass m, total mass m, and radius r is minus 3/5 gm squared over r. This is the value that Zwicky used in the 1930s. And together, what he did was he put together then the galaxy cluster mass of using the Virial theorem, using 2t. You can see I'm time averaged it now over a long period of time, and anything that you're measuring on cosmic time scales is time averaged anyway. because you are not actually looking at anything changing with time in the measurements you're making in this particular case. And then this is 0. So your V is just this, your GM squared over R, minus 3/5, etc. And then your T is 3 times, as I said, because you're measuring only one component of the velocity from the radial velocity. What you have to do is from the radial velocity, you have to subtract the mean velocity of the cluster, the Coma cluster. And so that gives you the velocity of the galaxy within the cluster. This is known as the velocity, dispersion. So this is why it's called sigma r squared. This is nothing but the radial velocity that you measure minus the mean velocity of the cluster, which, as you know, is the definition of dispersion. And so this is then your T. So once you put those things together, your minus 3/5 GM squared over R and 3 times, etc., plug this in, you get an equation for the virial mass of the cluster. And this is very simple. Just plugging these numbers in, you get the mass to be 5 times the radius times the average, the velocity dispersion, the radial velocity dispersion of the cluster. This is what Zwicky did. And he had measured many velocities, radial velocities in the cluster, and then together putting them together, he so this is what the Coma cluster now looks. I said this as always as a often as a assignment in my class who's doing learning about clusters or galaxies, etc. Now there are about 2,000 redshifts measured in the Coma cluster, and you can look at this. You can find the velocity dispersion, and then you do this, and the answer that comes out is about, as you can see, 4 times, 3.5 times 10 to the 5 times the mass of the sun, 10 to the 15. So if you look at this and Coma cluster, you do this calculation, you get 3.5 times 10 to the 15 times the mass of the sun. Whereas if you infer if you add up all the light of the galaxies and convert that to a mass, taking the ratio of the mass to the sun's mass, you get a few times, 4 times 10 to the 13 times the mass of the sun. So there's a difference of about 100, factor of 100 between the two. So that is the interesting thing. And what Zwicky pointed out from this particular cluster, of course, he did not have 2,000 redshifts. He had only 15 redshifts at that point, actually less than that, 13 or 14 redshifts. But even that told him that there is a lot of missing mass in the cluster itself, and the cluster is a very big system. In those days, until recently, those were thought to be the largest systems in the universe that are gravitationally bound to each other. And I'll tell you towards the end of today's lecture that we now know of such slightly larger systems which are called superclusters. But in the 1930s, when Zwicky talked about this, it was largely ignored because people didn't think that there could be missing matter. People thought that the application of the virial theorem probably is not proper, or he was missing something, or maybe his measurement of velocities was wrong, or something like that. So it was largely ignored. It was ignored till such things started being measured directly later on. And this started, for example, in the 1970s, when Xrays were found to in the cluster of galaxies from the hot gas that I talked about yesterday. The first X-ray telescopes went up in the 1970s and detected X-rays from clusters of galaxies. That was quite a surprise because people didn't expect clusters of galaxies to have hot gas in them. And then the question came, how is this gas becoming so hot? Again, you can actually have a virial theorem-like argument where you can say that if you know that there is dark matter in there holding the cluster together, then all these gas particles are sitting in equilibrium in this big halo of dark matter. And if you do the 2T plus V calculation, you will find that the kinetic energy of the gas particles will be very, very high. And if you then take the kinetic energy and estimate the temperature from it by using 3 kT as a measure, a thermal measure of the kinetic energy, then you will find that you expect the gas to be 10 to the power 7 degrees hot. And so this came much later after the discovery of X-rays. Now you can see I've chosen this particular picture on purpose to show you the impact of discovering X-rays from clusters of galaxies. It's the same cluster. On the left, something I studied quite a lot when I was a student, 3528. A cluster in the Shapley supercluster. And so this is a picture of the galaxies in this cluster. So if you look at this picture, you would not really see the actual distribution of galaxies that well. On the right is the same picture in which what I've done is I've made these galaxies into negatives, and replaced them with ellipses. Okay, so you can see that galaxy, that galaxy, that galaxy, that galaxy, that galaxy, that galaxy. I've taken out the stars, that galaxy, etc. That's that galaxy, right? You can see that. But on superposed on that is now an observation of the X-rays from the Rosat satellite, which had very low resolution. But this became one of the major images in their Rosat calendar every year because it's so striking. Because you can see that the smooth image of the gas that's in between the galaxies shows that there are actually two clusters in there that are merging together, like those merging galaxies. This, by looking at the image on the left, you would have never thought. You can't really see that. And that is because the hot gas maps out the distribution of actual matter in the cluster. And what is the actual matter? That's the dark matter. So if you then try and find out how much matter there needs to be in this cluster to have this much hot gas, and this is, but this hot gas, again, like I said yesterday, black holes is not dark matter. This hot gas is not dark matter. You don't see it in optical, but this is still baryonic, right? So this is still baryonic because this is mostly hydrogen in plasma form in 10 to the power 7 degrees. Right. So people do this calculation. And from the 1980s, once this was found, people did this basic calculation. And you can find this in most books now, textbooks now. You assume hydrostatic equilibrium. Yeah, just like you do the hydrostatic equilibrium calculation for stars, you can do it here. And you use the ideal gas law and think about this spherically symmetric kind of hot gas in hydrostatic equilibrium, and then you put in equations to do with thermal Bremsstrahlung, which is what is causing the hot gas, and this is the basic equations that is used. You can get the mass of the cluster. Just so out to a certain radius, you can measure the mass, and for that, what you need is the measure of the rho. D rho dr, which is the density of the hot gas as a function of radius, which you can measure directly from that observation that you saw. And then you have to fit some models to them to figure out the temperature at each radius of that emitting gas. And from thermal Bremsstrahlung models, you can do that. That it's quite a usual thing to do. And we have lots of students here who are doing this as part of their PhD thesis. So you have to have DTDR, which is, so here you have something like this. For example, take this one, this cluster, that's the central galaxy. From here, you can go in circles and find the temperature at each radius away from average temperature around an annulus. Similarly, you can measure the density and you can put these things in and you can get the mass. And once this was done in the 1980s, people realized that they were getting the same mass for clusters in the 10 to the power minus 15 solar mass range as Zwicky got in the simple Baryonic theorem calculation, right? That is when people started looking at Zwicky's work and then realizing that really clusters do have hundreds of times more matter than are in the galaxies, right? And this then becomes the predominant matter. It was also realized that that kind of matter cannot be accounted for by baryons alone. So people started looking for non-baryonic matter to become the dark matter. And you can see, for example, the Coma cluster that I showed you now, Zwicky's calculation showed 3.5 times 10 to 15. Now a better calculation is about 5 times 10 to 15 from more data now. The same cluster in X-rays, it looks like this. And if you look at the X-rays, you can see that the X-rays are centered on this galaxy. And actually, this is not the same scale. These two galaxies are both in here. This is a much larger scale, the Rosat image. These two galaxies are both inside the brown contour here. The X-ray gas is much, much bigger than that. And you can see there's a small group that actually we know now by detailed study that it's gone right through the cluster. It has fallen through. And all that you can see in X-rays. And just by looking at the galaxies, you won't be able to understand that. So that brings us to the third way of doing it. And you have already encountered this in Anuprita More and Sumit More's lectures, and that is gravitational lensing. Gravitational lensing provides, just a minute. Yeah, so now you can argue here, just like people argued in the case of Zwicky, that in the virial theorem argument, you are assuming that the cluster is in equilibrium. So there's an assumption there. And also you are assuming things will be spherical symmetric, all kinds of things. So it is to some extent model dependent. Here also, in the case of X-rays, it is model dependent because you are assuming hydrostatic equilibrium. You're assuming certain things about the composition of the cluster of the X-ray emitting gas. And in these measurement of dT/dr, you are fitting a model of thermal Bremsstrahlung to the gas to find the temperature from what you see is essentially the number of X-ray photons, and you can measure their energy, so you know their spectrum. So there are certain assumptions in that. But the way you can measure the masses of these clusters from gravitational lensing is a much more direct way of doing it without these assumptions. And that's what I'm going to do next. But before that, I can see people have questions coming. I can take a couple of questions. I can already see that somebody asked a question about globular clusters, and somebody's already answered it. So that's nice. Globular clusters are not underdeveloped galaxies. Galaxies have dark matter. Globular clusters don't have dark matter. Globular clusters are just collections of about 10 to the power 6 stars. That's a big difference. There's somebody who has asked, ISSAA has asked, plotting V versus R for dark matter, how far can we go? In R, the largest I have seen for spiral galaxies is about 5 times or so, but we can, as long as there are test particles, as I said, as soon as you go outside the continuous medium, which is the neutral hydrogen, then you can still go out. I mean, for example, in our galaxy, the stars stop at about 25 kiloparsecs, but you can go out to 220 kiloparsecs if you want, to the farthest satellite galaxy, which is Leo 2. Now, Leo 2 is 220 kiloparsecs, 10 times the distance of the edge of the galaxy in stars. But then the problem is that you don't know, it's just one object, and you don't know its orbit. So you can measure its radial velocity. So people have done this, and I've done this myself. You can assume many different kinds of orbits, and you can find the mass. It's not a circular orbit; it could be a straight line orbit. It could be. It could have more transverse velocity than radial velocity. All kinds of assumptions you can make, and you can come to some kind of mass measure, but from one single point, it is hard to do that. Anybody else has any questions? I can take one or two questions up to now in what I said up to now. No, if there are no more questions, I'll move on and very briefly talk about gravitational lensing, because this has already been covered in the gravitational lensing lectures. And I'll just motivate that in the context of clusters. You know that light bends in the while passing through space-time, and so space-time is curved by matter, and something that has been extensively discussed in previous lectures. And in Newtonian physics, of course, light could not have bent because light doesn't have mass. But here, light rays follow the geometry of space-time, and so it can actually bend near massive objects. Clusters of galaxies are the most massive objects. This thing can happen for stars, for galaxies, or whatever. And so what happens is that if you have a very distant galaxy and observing it from the Earth here, then as the light passes through and by a cluster of galaxies, it is bent, and you see distorted images, you see multiple images, and that helps you model the mass distribution in this system, which is called the lens. The lens being something that curves light rays, path of light rays. And so this is a direct method. This follows Fermat's principle. This has no underlying model and assumption in it. You're just simply geometrically doing this. So for single stars, this bending is of the order of micro arc seconds. And that is very barely measured. It can be measured by VLBI and things like that. As you know, the pictures that you've seen of the black hole in M87 has resolution of about 10 micro arc seconds. And that was done by interferometry using a very large array of radio telescopes all over the world. But already, if you're looking at the bending of light due to individual galaxies and their dark matter halo, that's of the order of arc seconds. That can be done, that has been done. Clusters of galaxies, this is much, much bigger effect. And so that is what is studied quite a bit very easily, because the resolution of even images taken from the Earth-bound telescopes is much less than an arc second. So you can actually study this. One of the most important things, and this you've heard in the gravitational lensing lectures, is that if, for example, if you have something like a source here and a lens completely aligned, then just from the symmetry, you can have light coming, having been bent by this source from all directions possible. There is no preferred direction, and so you should see a ring. And the radius of that ring can be worked out from general relativity. Actually, it can be worked out from basic geometry, but general relativity provides the actual accurate number here, which is 4. And it tells you what this ring would be due to the bending of light. And if it's perfectly aligned, you get an Einstein ring. This is called the Einstein ring. If it's not perfectly aligned, but slightly shifted, then this Einstein ring breaks up and you start seeing point objects, multiple images of the same object, right? And so these are good examples of such things. For example, this is a Hubble Space Telescope image of a almost complete Einstein ring around a galaxy. And so this is just one single source, and that's blue because it's a star-forming galaxy very, very far away. And you can see it completely warped, and you can see within this Einstein ring multiple images that are copies of it. Now, normally what you have is that these two will be not completely aligned, but it will be slightly misaligned. These are other Einstein rings. For example, you can find them in radio. So this is observed by the VLA. You can find them in optical and things like that. So the first multiple image like this was found by Bob Carswell in the 1970s. It was predicted in the 60s. This is a good example of the first one that was found, which is 0957, and two images found. And so you can say that, why do you think these are two images of the same thing? These could be two different quasars, very bright sources and they are being lensed by this galaxy that you see, which is in the foreground. But soon you figure out that you can have these four images. It's more common, Einstein ring, splitting up into different images. There are lots and lots of these. Now, how do you know that they are not four different sources, but one source? And that is because the spectrum itself actually shows you that they are identical. The spectrum is like a fingerprint to some extent. And you can see, and there's another thing that I'll come to in a minute, which also shows that these are essentially images of the same object, and that's the fact that you can measure a time delay. So in galaxy clusters, this effect can be huge. What can happen is that, and this is, I think, some of the most spectacular images taken by the Hubble Space Telescope with this exquisite resolution. I told you that the bending of images would be of the order of 10 arcseconds. So this is, for example, one of these clusters, Able 2018, which was the first one that was actually imaged like this, in which you have hundreds of galaxies. All the reddish galaxies are cluster galaxies, and the cluster is at a redshift of 0.176, about 0.2. But the images of these distorted galaxies that you're seeing are individually much, much further away. They may be at 0.5, 0.6, 0.8, and even further. So some of these galaxies are even at a redshift of 3 or 4, and they're very far away. And what you're doing is you're looking at very magnified and distorted images. And from each of these images, you can model the mass that is causing this distortion from the center of the galaxy. So in the center of the cluster, this is the central galaxy of the cluster, but the cluster extends to a much larger distance. And so you can find how much mass there is directly. No assumption of hydrostatic equilibrium, no assumption of thermal Bremsstrahlung, no assumption of any physical process. You're measuring directly the mass, the gravitational effect of the mass, right? And so this is a very, very interesting way of doing this. And I've had many students here model these things. So you can model the distortion caused to the image by the galaxies themselves, as well as the dark matter halo of the galaxy, plus the dark matter in the cluster itself, all together. So if you're modeling this cluster, for example, you first of all try you put in a mass as a function of R for the cluster. Then you have, say, the top 50 galaxies in the cluster, and you put them in where they are with a model around them and things like that, and try to figure out whether all the distortions of the individual things can be found from them. This is a very successful field. In this particular cluster, you can see, for example, this image, that image, and images on the other side belong to the same galaxy. Sometimes you see the same galaxy in 4 different places. So it's like in these systems where you see the quasar point object in 4 different places. But this is lensing done by a single galaxy. Here, lensing is being done by a whole cluster of galaxies. So the distortions are in a different kind, and the light bending is much more, and so you can get all these different things. So here's another reason why we think that that these images themselves have are from the same object. See, every object in the universe varies in light over time. Now, some things don't for millions of years, but there are many sources, particularly these very bright sources, which are called quasars, which are active black nuclei, which you heard about in Professor Saikia's talks. They have sometimes a very active black hole in the middle, a galaxy, and their mass falling into the black hole and things like that. So sometimes what happens is that they vary quite a bit in their luminosity at a particular wavelength. In radio sometimes in the optical, sometimes in the X-rays. And you can see that they vary in their brightness over hours, sometimes over days, sometimes over weeks. And you've heard about this in other people's talks, in the context of X-ray sources, in the context of radio sources and things like that. So if the source varies and they're coming to you at 2 or 3 different paths, or in this case, say 4 different paths, then if you look at the geometry of this, as I said, if you have 2 different images and the paths are different, then they're slightly different, right? The paths are not identical. Very tiny amount of difference. And then that is why if the source varies, then when you are detecting it, its luminosity will also vary. And they will vary at different times. So if you have 2 different images or 4 different images of the same source, then you will see them vary at different times. And this is, for example, one case, something a student of mine worked on, and this is the first double quasar that was found, I showed you. And here is a monitoring of it at radio wavelengths. I think we did this with optical and radio both. And so you can see that it is varied like this. This is its luminosity, and it varies. And then the other image, so this red corresponds to that image, this blue corresponds to that image, and this is the lens. And you can see the pattern varying, and this peak coming a little later, right? And the difference between them turned out to be, in this case, 400 days, something like that. So from that, you can find it. First of all, you can prove that these 2 are the same thing, right? You can't have 2 objects, the same part of the sky, too much of a coincidence, that will vary exactly in the same way, but one with a 400-day lag, or in some cases 10 days, 15-day lag with each other. And the second thing is it allows you to measure the actual geometry of the 2 paths, and thus it fixes your model. It allows you to measure the mass. It's actually a very interesting way of measuring masses and also measuring the distance to an object. And so this has been used now to measure the Hubble constant. It actually gives you an independent measure of the distance to an object for which you know its velocity. Okay. Now, these are examples on cluster scales, again, of these various arcs that are gravitationally lensed arcs. Remember, all of these huge arcs that you see are single galaxies, should be tiny, but just because the light from them are passing through this amazing distribution of dark matter, they are being stretched, and each of them give you very, very important information about the mass distribution in that cluster. All of these are from one single image of Abell 1689, which is a rich cluster of galaxies at a redshift of 0.2 or so, from a very deep Hubble Space Telescope from the ACS. So this is a wonderful field in itself. So this is called strong lensing. Why strong lensing? Because what you're doing is you're seeing one single source and they are being stretched. But on an average, what will also happen is that if you have faraway galaxies, they will also be distorted, if not strongly lensed, stretched like that, only in slight ways. And so that is known as weak lensing. So what happens is, for example, you can have a distribution of galaxies in the background, and you put a lens or like a cluster in the foreground, and you start seeing systematic effects of distortion, which is to do with the mass distribution. And you can already, in your eye can pick out systematic, but the galaxies are not all round, as you can see. And so from one galaxy, you can't really figure out the distortion if the distortion is because of a lensing effect or the galaxy itself is elliptical. But if you, for example, take a square like this and look at the average distortion of galaxies, you will find that there's something systematic going on. And these galaxies are all curved like this, these galaxies are all curved like this, and things like that. And that can be statistically quantified, and this has been done. So people do this quite a bit. So for example, if you have, for example, put down circles like this, you will see with a galaxy cluster and looking at the lensing effects, your eye can pick out. And this, of course, can be done mathematically to pick out how these are being distorted around it, right? And so this is known as weak lensing. And if the mass increases, then you can see starting from a very round thing, you can start. So you're not depending on individual galaxies, whether they're round or elliptical, you're looking at the pattern. This is known as weak lensing. And people do this for clusters. And people also do this line of sight for looking at how the light from a distant galaxy comes to you, how it might have encountered continuous mass distribution coming to you. This is known as cosmic shear. So large-scale structure, like the cosmic web, can also have gravitational lensing effect on rays that are reaching you. Okay, so this is a whole subject on its own. I just wanted to, I don't want to quantify it any further right now, but I just wanted to tell you that this is a very independent way of studying mass distribution in the universe, and dark matter can be mapped directly by its effect of distorting space-time. And so the light that travels through this distorted space-time goes and bends and creates these illusions. You can call them cosmic mirages. They are essentially making images look like what the original objects are not like. Okay, and this can be done on very weak scales, small scales, like small distortions of galaxies, but it can also be very strong distortions in which you see multiple images of the same thing, or highly distorted stuff, right? So all that, this is really a very direct way, and very little, very few assumptions go into the measurement of mass on this. Okay, so this is a way of doing this. So I just wanted to show you examples of clusters of galaxies where I told you about looking at the galaxies themselves in the optical, looking at the Xrays from the clusters and how the clusters tell you about the underlying mass distribution. I've told you about how from the weak lensing or the strong lensing of the images, background images you see in the field of a cluster, you can measure mass distribution. So here are examples of 6 different such clusters. You can see how clusters differ from each other in terms of their mass distribution. And if you take just one of these, you won't be able to. So here, just look at these. So these are the X-ray images of the clusters. These are the dark matter, the blue. The blue bits are the dark matter from weak lensing and strong lensing measures. So for the same clusters, and the actual optical pictures are on them for you to see whether the dark matter follows the distribution of galaxies. And you can see here's a blobs of dark matter, but the distribution of galaxies seems to be slightly different from each other. Here is the X-rays in the same galaxies, and here are all of them together. Now look carefully. You can see that in this particular cluster, there is this big blob of matter that the lensing picks up, but there is no hot gas there. All the hot gas seems to be in this blob. Here, there are 3, it looks like there are 3 clusters merging in a line, and the dark matter and the hot gas seem to be all following that. Here you can see, it's a very good example, which I'll show you in a minute, a little later. The hot gas and the dark matter seem to be displaced from each other. So here is a good example of how you need all of these observations to figure out what's happening in a system. This is where I talked about detectives and faint clues and things like that yesterday. And here is why you need multiple types of observations. Remember, these observations, these pictures were not just created like that. They come from years of observation, planning, and building instruments to make these observations with very different skills. X-ray observations are made by particle physicists. Actually, the digital camera that's used on the HST comes from technology that essentially then became the technology of the digital camera in your pocket right now, in your phone. These have evolved over decades. And so this is a good example. So I'll end this discussion. I'll talk a little bit about larger structures to end. But I just wanted to say that this is a cluster that you hear about quite a lot called the bullet cluster, which first showed this in a very stark way. The fact that the distribution of galaxies and the matter and the dark matter and the hot gas in it might actually, over short time scales, not follow each other. And this happens when two clusters merge. So here is what's happened. If you follow the blue bits, which are where the dark matter is from the lensing, those two have collided and have gone right through. And as they have gone right through the two clusters, the gas, which is a continuous medium, the hot gas has not gone all the way through. It's actually impacted and stayed in between. So these are two clusters that have had a collision, but the hot gas has been separated out of the cluster, right? Now, this is not a case where you would apply the virial theorem, like Zwicky, to find the mass of the cluster from the X-rays. Clearly, this is not in equilibrium. Also, the distribution of the hot gas is not following the dark matter. You can see example here. Whereas here, for example, you can see all of them, or even here, the distribution of dark matter and the hot gas seem to be on top of each other. So that's one lesson to learn from this exercise. And that is even on the largest scales that you can think of, which are megaparsec scales. These scales are a few megaparsecs across. There's a lot of action that's happening in the universe. There's a lot of, we talked about clusters merging. We talked about star clusters. We talked about galaxies merging. Now we can see the effects of clusters merging and interacting with each other. And the effects are seen very dramatically when you look beyond what you see in the optical images in the galaxies, and then you look through. So before I can see questions emerging in the chat box, and it's great that people are answering questions amongst each other. I'm going to spend just a little bit of time, 10 minutes or so, on larger structures, because that's something I work on myself quite a bit, superclusters of galaxies, and just try to sensitize you that what is happening now in this field of large-scale structures. And Asim Paranjape has talked about, in a statistical sense, in a physical sense, how large-scale structure forms in the universe in various dark matter models, and how that studying large-scale structures can tell you about the dark matter content of the universe. If you just go out and look at the distribution of galaxies, and you look at the distribution of stars in them, the distribution of hot gas, cold gas, and dark matter with lensing, you start figuring out that actually the distribution of matter in the universe is correlated over much larger scale than just clusters. Okay, so one of the assumptions you make in cosmology is that the universe is homogeneous and isotropic. Homogeneous means that it's on large scales uniform density. On what scales? It is not uniform density on these scales. It is certainly not uniform density in the scale of this room. It's not uniform density even on 10 megaparsec scales, right? So is it uniform in density over 100 megaparsec scales or even larger? This is a question people started to ask in the 1980s, 1990s. And the prediction from cold dark matter theories and cosmology You would find in the 1980s, when the first books in this subject were written by Padmanabhan, for example, large-scale structure formation in the universe, things like that, you would find that people were saying that you cannot have large structures beyond 10 megaparsecs or so, because dark matter theories don't allow it. But people started seeing these things. So, for example, 1985, already a large-scale structure around the Coma Cluster was discovered. I'll show you many images like this, so please get used to this. This is a wedge, which is a section of through a three-dimensional plot, and we are here, and you're looking out in space in distance. This is redshift, and this is RA, right ascension, one direction in the sky. So you're looking at a thin edge wedge like this, and you're looking out. So we are here, we're looking out. So, and we measure redshifts that we transform into distances. And so you can see that anything that is in the direction of the radial direction is stretched out because of velocity dispersion within a cluster. So this is actually the Coma Cluster. It looks like a person. They called it the stick man. This is, you can see, we are here. So that is one cluster looks like this in this particular diagram, because this is redshift, this is velocity. Actually, all of these galaxies are here, but they are stretched out because within the cluster, there is a lot of random motion. And so mean velocity plus minus, and you saw, I showed you in the Zwicky's plot, how there is a distribution of velocities within the cluster. And so that is reflected here, right? Similarly, you can see a cluster there like that. The clusters will appear like that. It will be radial. And so these are little groups, which have small dispersion in velocities. But anything that is transverse to your line of sight is a real structure, because you cannot, through Doppler shifts, make correlated structures. So this was, for example, first shown that there's a very large, and you can see there's a void here. There is this large structure. So here's something that came out of my PhD thesis in the 1980s, where if you look at this particular structure, that would be on this scale. And I found this big thing, right? And it turns out that within this big structure, there are 40 different clusters, right? And so you can see them here, etc. They all merge together, but it's much bigger. And the whole extent of this is about 30 megaparsecs or so. Here, the whole extent of this was about 5 megaparsecs. So the fact that you can have these big, so this is a redshift survey done by a student of mine who did this, and so each point here is a galaxy, and you can look at the even small clusters have associations with other clusters, and we call these superclusters. So superclusters can be very big, and we are now discovering quite a lot. So a lot of things have happened, and in the next couple of minutes, I'll show you a few examples of superclusters that have been discovered, which are much larger. The big question, are these gravitationally bound to each other? And that is something that we're trying to find out. It is difficult to find a structure that is 100 megaparsecs across, which has 30, 40 clusters in it, which are actually gravitationally bound so much that they're falling towards each other as the universe expands. That is probably not true. But locally, within this big supercluster, there might be 4 or 5 clusters that are bound towards each other. And they are all bound in a way that they are not expanding completely with the universe, but they're slowing down because of the gravitational interaction between them. And they're connected by these filaments. So these are essentially segments of the cosmic web. You can look at the cosmic web simulations where you see the matter on these filaments, and this very much look like the kinds of, and this is observation. This is observation in which you have actual measurements of the positions of galaxies, and you can see that it's beginning to look like what these simulations tell us. Here are, I had various students have worked with me over the years. Scott Porter did a wonderful thesis with me, where he identified quite a lot of these superclusters over, which are collections of 5, 10 clusters. And you can see that these are much larger scale, and these are real pictures. Real pictures, real plots from redshift surveys. So these are three-dimensional slices through three-dimensional distribution of galaxies. They look very much like the distribution of matter you see in the cosmic web simulations, right? Since then, in the last few years, there's some very good discoveries. This is the Sloan Great Wall from the Sloan survey, which is about 100 megaparsecs across the line of sight. So I said across the line of sight, they have to be real figures. And now, if you go to Wikipedia, you will see that people are talking about us. We are in the center of this particular part of the universe, and people are identifying these various superclusters. The Shapley, which is what I discovered 20 years ago, 25 years ago, is there. We are in the middle. The Centaurus supercluster, Pavo Indus, etc. So Pisces Cetus is something that I worked on quite a lot, etc., etc. So these are big structures of galaxies around us, and on the scale. So here to here, it is almost a few hundred megaparsecs. The distribution of galaxies doesn't seem very uniform, but one hopes that as you go out in space, you will see less and less of this clumpiness, and on a very large scale, this will be homogeneous. We haven't hit that yet, so this is an open question now. On what scale in the universe is matter homogeneously distributed? And what are the largest structures in the universe that you see? To me now, largest structures you see are these filaments of the cosmic web that can be many tens of megaparsecs long, maybe up to 100. So we now know that our own galaxy and the local group and the Virgo cluster are part of this very nice supercluster, which Brent Tully has named Laniakea. This is our home. We belong to a supercluster, and the Virgo cluster is part of it, and we are part of the Virgo cluster system, and we are falling into the Virgo cluster. The Virgo cluster is moving through this very nice system, and you can read about it. There are lots of work being done on our local supercluster. And you might also have heard that, here in IUCAA, we, Joydeep Bagchi and his group, I was part of that, from the SDSS, discovered something that we called the Saraswati supercluster, which is also one of these very, very big systems containing of about 40 such clusters. The difference between that and the others is that this is much further away. So this is at a redshift of about 0.3, whereas the other things that you saw in that plot of the Pavo Indus and the Pisces Cetus and Shapley, these are at a redshift of 0.05, 0.04. So they are at this scale in this wedge plot, and we found one that looks like this. So this got a lot of press because we had discovered this and called this Saraswati, and this Saraswati was named after the river in the sky because the Milky Way is Akashganga, and so this is and the people kind of had many interpretations of why we called it Saraswati. And I want to finish this by saying that that normally the general public doesn't pay much attention to what's happening in astronomy research. But sometimes, occasionally, something like this catches the public's imagination. So, for example, when this paper was published, and the fact that an Indian team had published one of the largest structures known in the universe, there were a lot of activity. We got tweets from many chief ministers saying, "We are very proud of you," and things like that. But the most important thing happened was that we became the last question in Kaun Banega Crorepati. So this guy was asked by Amitabh Bachchan as the last question on Kaun Banega Crorepati, what was the name given to the supercluster of galaxies? Now, you will be able to answer this question now, but this guy wasn't. He lost half a crore because at that time, the prize money was still 1 crore, right? Okay, so I'm going to stop there. And with this example of how you can earn money by knowing a little bit more about astronomy sometimes, or lose money if you don't know the answers. Okay, thank you very much for listening to this, very rapid description of how to measure and detect clusters of galaxies. Let me see if you have any questions on what I talked about in the last couple of days. Looking at the chat box, if you have any questions, raise your hand. I can answer questions, or you can unmute yourself and ask questions. Rabiul Islam says, it seems from the pictures that the dark matter surrounds observable matter. That's a very good observation. Since nobody's asked any questions yet, let me talk about this a little. See, what should I? This is a good example. So here is, I didn't talk about this. This is a very interesting plot made of the nearest 10,000 galaxies, to the Milky Way. And this is just a projection on the entire sky. The whole sky is projected in this circle. And you see this place is missing because that is where the Milky Way is. We can't see through the plane of the Milky Way. So this is just missing because of our inability to look through the plane of the Milky Way. So forget about this. This is not a real effect. But what you see outside is that there is this nice plane of galaxies. And that's called the supergalactic plane. And that's absolutely right. Actually, the Laniakea supercluster comes from this. It is such that you saw the picture of the Laniakea supercluster. It's also a planar structure. And this is the plane of the Laniakea supercluster. And it goes out to very high distances. Now, independently, you can see where we are going with respect to the rest frame of the universe. The rest frame of the universe is given by the cosmic microwave background, right? Because it is attached to the universe. As the universe expands, the actual the frame that is attached to it must be the energy that came from the Big Bang, and that is the same V. So we can measure our motion, the motion of our galaxy, the motion of our sun, and then our galaxy with respect to the cosmic microwave background. And that tells you which direction we are moving in the universe. Yeah. Now, on large scales, our galaxy has to move in the direction in which it is being pulled, right, by all the other objects in the universe. Okay. So, and it turns out, if this is the nearest 10,000 galaxies, we are being pulled right there. So that is also telling you, now that's nothing to do with the light that you see here. You see only the galaxies that you see in light. So we are going in the universe in a direction in which we also see is the largest concentration of galaxies, right? In the plane of the local supercluster. That tells you on the large scale, this is called the cosmic dipole. And the cosmic microwave dipole you measure from the cosmic microwave background. We didn't talk about this, and I hope people who talk about the CMB have talked about this. It just tells you that these are two independent measurements. One measurement is looking at the distribution of galaxies, and another measurement is looking at where we are going in the universe. And these two are aligned with each other. And that just means that the dark matter is distributed in the universe where the galaxies are. Where there are voids in between the distribution of galaxies, you don't expect to find dark matter. This is one good observation. And so that is a good question that you had asked. Anybody else has any question? Yeah, Shriya's question about a halo scene in Hyderabad, I have no idea, frankly. I mean, it's nothing to do with what I talked about here. And the rainbow halo, etc. I mean, there are quite a lot of atmospheric effects that you can look about. What happens after rain? There are some lovely halo effects something called sundog, for example, which come from the sky. You can read about them. This is atmospheric physics is a wonderful subject. It's nothing to do with me. Anybody else? Okay, it looks like there isn't much of questions. Jyotirmoy's question has been answered very rightly by Astha. And Jyotirmoy's question was color between two images in the same source are different. Why? I probably told you this before, that in astronomy, we don't take pictures by color cameras. No images are taken that color because color cameras are a cheat. Color cameras are not real measuring systems. They are created to give you satisfaction that you're taking color pictures. You can't really make measurements from color cameras. So normally cameras that professionals use take grayscale images, and what you do is you take it with different filters. I use a red filter, I get a gray image. I give you a blue filter, I get a gray image. And then you mix colors with them to create the color image that I'm showing you. So different people do it in different ways. That is why you see the same so-called color image of a galaxy or a cluster or whatever coming from different sources, having different colors, because nobody takes a color image. All color images are false color images in astronomy. Let's see, Shubhajit Paul is asking, is it found yet why there is a web-like structure? No, web-like structure is just been discovered maybe 20 years ago. Why is it a web-like structure? We don't even know if it's a web-like structure. That's what we see in projection. It could be a sheet-like structure, right? It could be in three-dimensional, very different kinds. And we haven't really, like nearby in the 3D distribution of stars, we have Gaia, and we can make 3D models very reliably. In distribution of galaxies, we don't have very reliable 3D models, 3D observations. So we don't know what the structure is like. That is a very interesting question that will have to be certainly be studied in the study of large-scale structure. I have no idea about DNA-based dark matter detectors. Okay, so I've looked at all the questions in the chat box, and it looks like there aren't any other questions. So I'm going to sign off. Thank you very much for being with us, and I hope you enjoy the rest of the course. Thank you.